Hello, I'm Bill Spence, Professor of Theoretical Physics at Queen Mary University of London. I'm an editor for Culturico and your host for this podcast. I'm delighted to introduce our guest today, my colleague, Professor David Berman. David is a highly successful researcher in string theory and, as well as this, has an outstanding record in public engagement. His work linking science and art is particularly notable. We might not have time to cover this today, but I do recommend you look this up as well. David has broad intellectual interests at the forefront of research, and today we're going to discuss a field that is rapidly growing and is transforming how we think about doing scientific research, in physics in particular. And this is the recent use of machine learning and artificial intelligence to advance work in theoretical physics.
The aim of Culturico's podcasts is to provide the listener with an artistic, yet realistic mosaic of human pictures. Macroscopic events of our society result from a complex combination of individual dreams and ambitions. We provide stories that have humans as their core element, from macro stories about our multifarious culture, including politics, society, and science, to micro stories of individuals' hopes, struggles, and change. Our stories are told by people with their own life experiences, beliefs, and reflections of past and present events. We therefore provide a multifaceted image of our world, observed and understood from different perspectives.
So, David, let me start by asking you, after some decades in string theory research, how did you get into this field?
So many years ago in the 90s, I was working at British Telecom Research, and they were very interested in neural networks for all the obvious reasons. As a telecoms company, having that idea of machine learning and artificial intelligence was an area that BT really wanted to study. But in some sense, it was too early then. But I was exposed then to the enormous industrial potential that machine learning had. And then almost 30 years later, there was this discovery moment when AlphaGo beat the world champion in Go in the most amazing way. And that sent shockwaves through the community of people who knew about artificial intelligence, because Go was always seen as this game where just brute force of computing power would not lead to dominance. And yet, here was this way in which a computer had come and, using neural network methods, had beaten the world champion. After that happened, there was a whole bunch of people who thought, what's going on now? What have been the developments in this area? And it sparked a whole load of interest throughout the world, and I was part of that.
I mean, for people who don't know much about this, how does a machine go about playing Go? I mean, what is artificial intelligence? What is machine learning? What actually happens?
So let's separate off two things. Artificial intelligence is a little bit more broad than machine learning. Artificial intelligence is where you want a machine to be intelligent and have all the aspects and attributes that humans have. So that's a very broad thing. Machine learning is a little bit more specialized, and as a result, allows us to be more scientific, if I can use that word. What you do is ask the question, can you take a set of data and learn things from it? And what they did with AlphaGo and subsequently various chess games and so on, it wasn't that they gave the computer an expert knowledge of chess. It wasn't like you just took the world's best person at chess and then told the computer what those rules were. You gave the computer games and had it play games and learn like a human would. And that's what machine learning is that you present data and then you have the machine learn from the data. It has a cost, which is that you don't know what it's learned, in the sense that when you teach it an expert system, you know what you've taught it. When you present it the data, the machine infers from the data how to play, but you don't know exactly what those rules are that it's learned.
And how does that work? How do you actually train the machine? I presume you reward the machine in some way when it gets things right, and then you should if it doesn't, and so you push it towards being clever.
Yeah, that's right. So perhaps I can explain a little bit how machine learning works in general, which is that you have something called a neural network normally. There are other ways of doing it too, but let's look at this very commonly used thing, the neural network. And you should think of a neural network, as the name suggests, as something based and inspired on the brain of a whole bunch of neurons, which we'll call nodes, and their connections, which in the brain will be synapses, are links between these nodes. And the nodes get stimulated by data, and then those stimulations get fired along the connections to other nodes, which are called weights in the neural network language, and they will fire off other neurons or nodes. Now, when you first start, you have this to be a random thing and so on. What learning is changing those weights, changing the responses of the synapses to the neurons firing to replicate the function that you're interested in, to replicate behavior and so on, so that this network of things firing can replicate a behavior or a function based on some inputs. And the way that you do that is indeed this idea of training, that you say you've got a goal, you've got something called a cost function, and basically you move the weights so that the cost function is made as small as possible. And the cost function is basically the difference between what the network does and what the data shows it. There are other ways too. What I described there is something called supervised learning, which is where we know what's right and wrong. We know what a cat is or a dog is, and then you try and teach it that thing. There's another way called unsupervised learning, where it will naturally learn groups of things. If you show it the numbers from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, it will automatically spot in handwriting groups and group together all the zeros into one group, all the ones into one group, and recognize, just as a human would, without being told this is a zero, when you see 10,000 zeros, you know to group them all together as one object. And that's another way in which machines can learn.
I mean, these seem very complex problems. I mean, is it the case that these networks have sort of layers, so that the top layer learns some sort of rough idea of how to play, and then the next layer sort of abstracts from that into something a bit more detailed?
Yeah, so one of the big developments was going what they call deeper. So the depth of a network is coming back to this, and take this picture really of a brain, of nodes connected by synapses, of neurons connected by synapses. And instead, you've now got these nodes, and then they go through a weight to the next node. And then you can ask yourself the question, how many deep do you go before you stop? So you go from one node to the next node to the next node. Each time you go an extra node along, that's an extra layer. Now, computationally, in terms of implementing this on your computer, we can do this now. It's no problem. But back in the 90s, when these things, or in fact, these things were actually invented all the way back in the late 60s, it was enormous computational cost. You couldn't run these things on any sort of computer in the day in any finite time as you went deeper, because the complexity as you go deeper with all the different connections blows up exponentially or exponentially of exponentially. So what changed, what made it work now or a few years ago, was that computers got powerful enough so that we could run deep networks on ordinary machines. Back in the 90s, you need a supercomputer, or you'd be restricted to 1 or 2 layers. Now they can run it 100 layers deep. And this is this thing that they've got, which is called deep neural networks. And that gives the neural network the capability to learn very, very complex and intricate and detailed functions of how to behave.
Mm. I mean, this is a topic we could go into for hours. Let's talk about how this interacts with physics. I mean, how does this actually interact with physics?
Yeah, so there's 2 ways. Of course, physicists will think, is this a tool for us? Can we use machine learning to aid all the things that we do in physics? And so let's look at some examples of that. Now you can look at the night sky and with a telescope see hundreds of thousands of galaxies. But an astronomer can't sit down and classify 100,000 galaxies. So one of the things that you can do is use neural networks to help classify the type of galaxy that there are. And so rather than have a human sit down and by eye look at an image and go, that's a spiral galaxy, that's a globular cluster, you can take these images and automate the whole thing. So that's an example of a classification problem that a human would normally do that's a bit tedious. And what you want in the end is just the statistics. How many out of the 100,000 that you've observed have this property? And machine learning can do that and has done it very successfully. But then you can think the other way around. Can physics help machine learning? And this is really the area that interests me more. And it has a long history in machine learning, actually, in computer science. Yeah, there was a very famous physicist called Stanislaw Ulam, who left Poland and joined the Manhattan Project, which, of course, very famously came up with a nuclear bomb. Perhaps science is not the greatest moment, but it was certainly a collection of great minds. And Stanislaw Ulam, during the Manhattan Project, for whatever reason, broke his leg and was hospitalized for weeks on end while this leg healed, during which time he played the game Patience, which, you take your cards and you rain it out and do all these things. And he asked the question, what's the chance of winning a game of Patience? Now, you think that would be easy. And then he hit upon the problem it wasn't really easy to tell at all. So then he thought, well, you just work it out. You just look at all the combinations of a pack of 52 cards and count the ones that win and discard the ones that don't. And then you know what the chances are of winning a game of Patience with perfect play. Your problem is this. The number of permutations of a pack of 52 cards is more than the atoms in all the universe. So you can't do that. So he hit upon the idea that what he wanted to do was a clever sampling of the pack of cards that would reflect the chances of what happened. And this is what has since become known as Monte Carlo sampling. It was named Monte Carlo sampling because Ulam's uncle was a very keen frequenter of casinos. And it relies on randomness in its sampling algorithm. Randomness is something which physics copes with very well through the laws of thermodynamics and statistical physics. Now, I mention this story because at the heart of some machine learning algorithms, people use this sort of sampling and this sort of idea that what you want to learn is a probability distribution, but you can't do it exactly. And so they use the ideas of statistical physics and the ideas of someone called Boltzmann. And when you're describing a probability distribution, then you emulate it as a physical system of the type that Boltzmann discovered and used. So a good example of this, Jeff Hinton, who's one of the so-called godfathers of AI, he's as big as it gets in AI, constructed these things called Boltzmann machines. And a Boltzmann machine basically replicates any probability distribution as a physical system based on statistical mechanics developed by the physics of Boltzmann. And then he applied that, and using that, he could do handwriting recognition. It's at the heart of the algorithm Netflix uses to recommend you films. So in there, theoretical physics has developed a whole set of tools that are useful outside of the realm of physics. And machine learning has locked onto those.
Is the physics telling you what's going on inside the neural network, inside that black box? Is that
very, very good question? So, as I said, when we teach a machine through this training process, we don't know what it's learned really from the process, and there are many examples where shocking things happened. And this thing of what's called interpretable AI or interpretable machine learning is a very important thing that's going on now. And I'm going to give some examples to put it into context. And yes, the hope is that physics will provide an insight as to what the black box is doing. But let me explain first with some very trivial examples of what goes wrong, and then with some very non-trivial ones. So there's a famous case of the US military wanting to use machine learning to identify Soviet versus American tanks. Now, and so what you do is you go back to the data. They take all these pictures of Soviet tanks and they take all the pictures of American tanks, and then they run it through this network and it learns something. And then you show it a picture and then it determines whether it's a Soviet tank or an American tank. And then, if one was not careful, one would then use that algorithm to determine some dreadful action that would then take place. Fortunately, people tested this a little bit after it was done, and they found that at first it perfectly identified all the Soviet tanks and didn't have any of the American tanks, until they did one thing. They showed it an American tank in the snow, because it turned out all the pictures of Soviet tanks were in the snow and all the American tanks were in either forests or desert. So what the machine had learned was that if something is in a white background, it's Soviet and bad, and not otherwise, because that was the biggest thing to see. And so it's like taking a child and saying, good, bad, good, bad, good, bad. And then the child goes, oh, if it's in a white background, that's bad, because that was everything I'd seen. And so what one is seeing is that when one selects data sets to teach, you have to be very careful, because you've got to control for all of these background effects, which are not the things that you want it to learn, which is it in a snowy background or not, and learn some complicated thing about tank tracks or God knows what. So people then, got worried after those sorts of things. And then there were other ones which are very similar, actually, in their problem. I forget which company it was, but it was a major one, launched an AI Twitter feed where it was trained on Twitter. And the idea was it would pass a Turing test that you wouldn't be able to tell it apart from a human being on Twitter. And then what happened was it spewed out enormous amount of racist and terrible comments. So maybe you couldn't tell it apart, but this was not the behavior the company wanted as its representative. And it had not done anything wrong in what you taught it. All you'd done is trained it on Twitter feed. You'd not given it a much bigger cultural background about what's good and bad. So there is a huge danger, because you train on limited data sets without greater context, whether it be the weather that tanks are in or a human being part of a cultural norm, that the results can be very bad for what you want to achieve. This is why interpretable AI is so important. And then as a very practical need, we use AI and machine learning to do very useful and practical work on things like cancer diagnosis. You take NMR scans and then you feed this in, and then through machine learning, you can then predict, hopefully, where there might be tumor versus benign things. Now, medical councils are very careful. You can't just have something that is deemed to work. That's a dangerous precedent to set for a medicine or something like that. You need to know why. So now medical councils will not allow even diagnostic tools without an understanding of why. So it's crucial that we have an understanding of the machine learning black box. And yes, there is a hope that physics can provide that by explaining the mechanisms by which you extract and learn from data. What aspects are you learning? What is the process of learning? And in doing that, that also helps training, and it helps a whole bunch of things.
Well, I assume when you're training, you have to be a bit careful, perhaps not to train too much, because then it'll only recognize things in a very specific way. I mean, you might not get the learning you want. You have to be careful what you have to know what training or what, as well as what to train on.
So what you're describing is something which is called overfitting, which is where you learn the exact data, but not beyond it. So let me give a good example. And it even exists as a neurological disease. There are people who have such perfect memory. This is described in works of Oliver Sacks, where you have a perfect memory, and the result is you can't recognize people because the person that you recognize, that you see again, doesn't look exactly the same. They're not wearing exactly the same clothes. They've got a haircut that's slightly different, whatever it may be. So they're different. So if your memory is completely perfect, how do you recognize someone? Now, of course, as a human, what you do is you learn to identify salient parts that are more important than others and ignore a whole bunch of other things that might change. And if you think about it, it's quite an amazing trick that you can recognize someone. You could distort them in all sorts of ways, and I'd still recognize them. And so what's going on there? So it's that, and this is what you want to emulate in machine learning. You don't want it to just learn something exactly, because that won't be extendable the moment any little thing changes. You want to them to come up with a model of something that can be quite robust, meaning lots of things can change and it's still a good model of that thing. So one of the ways that you do that is, it's a very traditional philosophical statement of Occam's razor. So Occam's razor is, don't make the model more complicated than it need be given the data. So what you do is when the machine is learning and you reward it for matching the data, you also penalize it for if the way it matches the data is too complicated.
Oh, that's interesting.
So you say, no, you've matched the data really well, but you've done some ridiculously complicated way to do it. So you penalize that. And then the machine learns it can't be too complicated in its models. When it does that, then that model is more flexible and more robust to change and so on.
It's starting to sound like what a lot of scientists do, in that they try and understand some phenomenon and they're looking for a simple way to do it. Not, you can probably describe anything with a suitably complicated model.
Of course.
And scientists are looking for something that's coherent and fits with other things, but is also quite simple. I mean, to what extent are these machines can they make their own theories in the end? Can they start inferring a new way of understanding knowledge in some sense? Or, are they getting to the point where they're doing a lot of what scientists do in that more sophisticated sense?
In some sense, this is a very philosophical question. As you say, a theoretical physicist makes a model of nature as simple as possible. It's not that we describe nature perfectly, because you could, and that would be a stupid thing to do. That would just be writing down all the data and then listing it, and that's not what you do. You write down a simple law, F equals MA, F equals GMM over R squared, and then from that, you describe all the motion of the planets. And that's ridiculous when you think about it. The complexity of the motion of all the planets compared to F equals GMM over R squared. And that's what has led to the success of physics, that we've had this period where we could use simple mathematics to describe so much of the universe. And it's been amazing. The more you know about that, the more it's amazing when you think about it. Now, machine learning won't do the same thing, in the sense, to be quite careful, it won't come up with a mathematical law, but it will come up with a mathematical model. And it's possible it could model something that you can't come up with a simple analytic law, but it could still model it well. And now you've got to decide as a physicist whether you're happy with that. Are you happy with a model that's not something you just write down an equation of, if it can describe a whole host of behavior and do a whole host of things?
Most of my colleagues would say no, but if it works,
indeed,
we should.
But if it works, maybe one should think about it.
Yeah.
But provided we understand how the model was arrived at and what's gone on. But, let me give an example in number theory, in mathematics. For years, people wanted to understand the distribution of prime numbers. And it's very hard to know when the next prime number is coming and predict it. It's not an obvious thing. You got to do tests, filter them out, and so on. And then people changed the question a bit. They asked about what's the density of prime numbers? What are correlations on prime numbers? How pairs of prime numbers might occur with probabilities? And then you can do that. And I think it's possible machine learning is a little bit like that. You may have to accept that there are some descriptions of things that are not perfect and analytic, but are probabilistic and built on, in the end, if you're right 99% of the time or 99.9% of the time, do you worry about the 0.01% that you're wrong? And then are we happy with that as a description of a law of nature? Because there could be loads of things where it's impossible to write down an analytic thing. You bang your head in some very complex behavior of how proteins unfold, how galaxies interact, et cetera, the three-body problem, three bodies you can't solve classically. But what if I can statistically tell you, given things in a certain round, the likelihood is the following thing, and the machine can learn that?
Yeah, you'd probably take that.
You'd take it, provided you understand how it got there and what's going on, and you put on bounds and so on, and you understand these things. So there is, for the future, not for all of physics, not for all of science, but it's opening up a new way of approximating and modeling nature. We went through a period where we used the power of mathematics to analytically write down things precisely, and that was the era of Newton. We went to statistical physics in the 19th century, where we would then write down systems with infinite number of things and just describe them by a temperature or something. And then we've always had this problem of that intermediate thing, not between one or two bodies, not an infinite number of things of gas, but when you've got 100 things interacting. What do? You normally just give up, and it would never be taught in a physics degree. And you would just go, I can't cope with 100 things. It's not big, it's not small, it's interacting a lot. I don't know what it does.
It's almost like a new branch of science in a way, isn't it?
It is. It's the realm where, as I say, Newton worked great for a small number of things. Traditional statistical mechanics work great for an infinite large number of things, and its effective description, like gases. Now we're moving into what you do with 50, 100 things strongly interacting. There'll be some emergent phenomena, but it's not so many you can make the approximations that were made in the 19th century.
Let me come back to mathematical physics and this interface with machine learning. You run a weekly seminar here in London. What are the sort of the hot topics at the moment, and where do you plan to carry on your research in this sort of area?
I mean, we've had a lot of talks on a very diverse set of things. One of the things that has struck me is the interest of young people. I'm now at the age where I can use the word young people. And a lot of people who have insights, who have knowledge coming through and are looking at machine learning and are going, there's so many areas here that we can contribute to. So we've had things about tropical geometry, which was a very obscure area of mathematics. Turns out to become related to complexity in neural networks. We've had discussions on machines learning mathematics themselves. We've had discussions on Boltzmann machines, which I've already mentioned. That there is this feeling that there's so much out there, and that what theoretical physics developed over years is this enormous tool set that's got great power. In terms of what I'm doing, there's a different set of things. I'm very interested about the learning process. And that learning process can be related to things in quantum field theory, like something called a renormalization, which is sort of quite difficult to get into. But let me just say, it's a process related to how we understand different scales of nature being related to each other. And that those different scales in nature may well be related to how we learn in a neural network.
Great. I'm afraid we have to end it there, David. Thank you so much. This is such a fascinating story. It's just a glimpse of what's going on, I think. What struck me in this conversation is how rapidly these new ways of computing are being utilised in scientific research. They really seem to be turbocharging the generation and testing of new hypotheses, and often in quite unexpected areas. And now the string theorists are involved. Who knows what will happen next, right? Many thanks, David, and all the best wishes for your future work in this area. Thank you.
Thank you. Thank you, Bill. Bye.
Thank you for listening. This episode of Culturico was produced by Bill Spence. You can find his writing and our latest articles on science and culture at culturico.com. To get our latest episodes, subscribe to Culturico on your podcast platform of choice. And if you like what we do, feel free to give us a review or spread the word. It means the world to us. Thank you, and until next time.